Hello, welcome to India's most comprehensive e-learning platform, BYJU'S Exam Prep. In this great evening, we all have gathered together to discuss one of the very important topic in optical fibers. That is, in fact, optical fibers is the topic we are going to discuss in the special subject that is optical instrumentation, and it is exclusively for instrumentation students. Probably all instrumentation students are very much aware of the importance of this subject. Every year in GATE examination, especially from this particular subject, you will be getting at least 4 to 5 marks, and if you are lucky enough, you may get even 6 marks also. So, as keeping the weightage of this particular subject in the mind, we have designed almost around 2 sections on optical instrumentation. Probably if the students demands more sessions related to champion series, especially in this particular subject, we are ready to take that. However, in this particular topic and in this particular session, we are going to discuss about optical fiber, which is exclusively important in this particular subject. Of course, it will also have the weightage of 1 mark to 2 marks. Mostly it would be for 2 marks. So, let me try to cover all important topics in a very concise manner, so that you all can perform very well in the final examination. Before going to discuss the questions related to optical fiber as a part of the champion series in the subject of instrumentation, of course optical instrumentation, let me quickly introduce about myself. As you all can see, myself Phanindra, all put together, I have an experience of 12 plus years in teaching industry, guiding for GATE students as well as for ESC aspirants. Up to now, I have guided more than 50,000 students in the subjects of control system, circuit theory, industrial instrumentation, and even optical instrumentation also. Clear? So let me quickly share the schedule of the optical instrumentation. As you all people can see, there are 2 lectures which I have taken. In fact, 1 lecture I have already completed in yesterday's session, that is light sources and detectors, where we have clearly discussed the questions related to the LED and laser. Followed to that, we have discussed some questions related to LDR and then pin photodiode. So more or less we have covered all the topics which are there in the light sources and detectors according to the instrumentation GATE syllabus. In this particular lecture, we are going to give maximum our attention to the special topic, in fact most valuable topic, that is optical fiber. Basically, optical fiber is nothing but a transmission medium. It will pump or it will allow the light ray to flow through it, and finally it will take the light from the source and land the light at the detector. So obviously, being an instrumentation engineer, you must know how optical fiber construction looks like and how optical fiber will function and in what way the light will be propagated through the optical fiber. More or less, you might be knowing very interestingly this point that optical fiber is going to work on the total internal reflection. Clear? So this is the main principle which you must know before going to solve the questions related to optical fiber. However, you all can connect to me through this Telegram credentials. If anybody want to know the instrumentation topic so deeply, especially to the GATE syllabus, not only about the GATE syllabus, even after GATE examination, if you want any special assistance or special guidance for the interviews or else interview experiences, then you can contact me at any particular time. So I will be always ready to help if any student from instrumentation student, if he is very sincere. Clear? So moving forward, let's discuss about the statement of the first question in today's lecture from optical fiber here. So the statement is clearly mentioned that an optical fiber has a numerical aperture of 0.20. Clear? And a cladding refractive index is 1.59, that is given as N2. The acceptance angle for the fiber in water, which has a refractive index of 1.33. So in fact, it is water refractive index, NW is dash. Clear? So these kind of questions are very famous. If you go and refer the previous year questions, you will be having at least 2 to 3 questions related to this particular topic. So let me straight away solve this question from very fundamentals. So if you take any optical fiber, every optical fiber will have a particular numerical aperture, correct? So usually the numerical aperture we denote like NA, and for every optical fiber, the numerical aperture will be calculated by taking air as a reference medium. I repeat, air as a reference medium. However, the numerical aperture will be given by the manufacturer. It will not be changed according to the surrounding medium. Remember this, its value is fixed, it will not change according to the surrounding medium. Clear? So therefore numerical aperture can be given as equal to under root of n1 square, where n1 is the refractive index of the core, minus n2 square. Clear? So let me write down very clearly, as it is the first question. So n1 is the refractive index of core here. Of course n2 can be written clearly as refractive index of cladding here. So n2 value is given, but n1 value is not given here, correct? So n2 value is how much? 1.59, but the numerical aperture is given, and you require first to evaluate the refractive index of the cladding here, core, right? So if you have the refractive index of the core, then obviously you can calculate the required value very easy. It is not required, just I am calculating for your understanding purpose. Okay, so moving ahead, so you can see here numerical aperture is how much? So I can say this is 0.2, correct? So 0.2, let me square this one, so it will be having like n1 square minus n2 square here. Therefore from here I can say n1 equal to, what will going to happen here? So this will be 0.2 whole square, of course, plus n2 square here, correct? So therefore what should I say? The refractive index of the core could be written as under root of 0.2 whole square here, plus what is the value we are having here? N2. N2 is the refractive index of the cladding, that is nothing but 1.59 whole square here. Now be relaxed and tell me what is the value of this one. Anyone, if you calculate, let me know. Pramit, just sin inverse sales. Yes, that is correct. So as this is the first question, I am going slowly. So if you are having patience, take your calculator and tell me what is the refractive index of this one. So the refractive index of the core. So what should I say here? Of course under root of. So Pramit has given almost the answer, but I want everybody of you to solve this question. So plus what will be the value? 1.59 whole square, correct? So this will come down to be equal to 1.6, approximately 1.60. So two things you must understand here. The number one, the very first thing is the refractive index of the core. After a lot of hard work, we got like refractive index of the core is equal to 1.60, and the refractive index of the cladding is equal to 1.59. Obviously, I should say refractive index of the core will be more than refractive index of the cladding. Now, tell me, how do we calculate the acceptance angle for the fiber in water? Pramit, what is the answer? So, I want the answer from you. Take the calculator and do it and let me know what is the final answer. Don't tell me how to do calculation. So, please let me know what is the final calculation here. Pramit, so the acceptance angle may change according to the medium. Generally, if air is the medium, if air is the surrounding medium, then the numerical aperture is straight away can be calculated as numerical aperture is equal to refractive index of the A, that is n0, into sine theta A here. Clear? So where theta A is considered as the acceptance angle. Clear? Theta A is considered as the acceptance angle. And as I was saying, numerical aperture will not change according to the surrounding medium, because numerical aperture is a figure of merit given by the manufacturer to the customer. Clear? So suppose if I say the resistance value, so the resistance value, if it is manufactured, is provided at a particular temperature, its value will remain same. Correct? Similarly here numerical aperture will be the same. But if the surrounding medium is water, what should I say here? If the surrounding medium, if water is the surrounding medium, now you should be very careful and rewrite this one. If the water is the surrounding medium, I am absolutely sure that it has to be rewritten as numerical aperture. It must be equal to the value of the water refractive index into sine theta A. Now you see, even in the first case we are using the same numerical aperture. Second case is also same numerical aperture we must use. Whereas the acceptance angle in the first case and the acceptance angle in the second case both will be different. So if you want, you can even write down this is the acceptance angle in the air and this would be in the water. Clear? So therefore, it is very easy to calculate from here, because almost I have done 90% of this question and Pramit has already given the answer, but let me explain, because there might be many students who will come and watch the lecture after the live session. So for them, at least I need to make it. So therefore, sin theta W, how can I write this one? That is acceptance angle when the fiber is in the medium water. So it would be equal to numerical aperture divided by NW here. Clear? So theta W must be written now as sin inverse of numerical aperture divided by NW here. Correct? So that means refractive index of the water. So that could be written as a sin inverse of 0.20 divided by refractive index of the water is how much? 1.33 here. So be relaxed and tell me the final value. So let me do it for every one of you. So this value will be equal to 0.2 divided by 1.33, and you will be having some value like 0.150. So sin inverse of 0.150. So it will be coming like 8.6. Correct? So 8.6 degrees, such a very, very low value here, right? So the final answer will be 8.6 degree. Now Pramit, I want to ask a question to you. Just think logically and tell me why the numerical aperture of the fiber remains constant. Clear? That is one question. How do we change the numerical aperture of the fiber? So that is the second question. Any question you can answer. This is a bonus to you, Pramit. How do we change, or how can we change the numerical aperture? Is it possible or not? Just think and tell me. So of course, the final answer for this question is, as I was saying, it is going to be equal to 8.6 degree. Now moving to the second question, that means in the previous question itself, I mean from the statement of the previous question, we must solve this one. Because if you see, even in this question, the statement is mentioned like numerical aperture is 0.20 and cladding has a refractive index of 1.59. But however, the critical angle at the core and cladding interface is dash, right? So Pramit, yes, we can change by changing the medium. We can change by changing the material which we used for the optical fiber. Clear? So the numerical aperture can be changed only by changing the material what we are using for the fiber. If we change the medium, the numerical aperture cannot be changed. So remember this point, Pramit. Okay, only acceptance angle will be changed if we change the medium surrounded by the fiber. So now the critical angle at core and cladding interface is going to be dash. So to answer this, so you must understand anyway. So suppose let us say we are having the core of the fiber like this. So let us assume that this is the core of the fiber, right? And maybe this is the axis of the fiber. So as I was saying, this is considered as a core of the fiber. However, we do have like a cladding here, correct? So let us say this is going to be considered now as cladding here. Clear? So this is considered as a cladding. Undoubtedly, even below also we will be having cladding only. This is also considered as a cladding. That means cladding is completely surrounding, or the core is surrounded by the cladding. The core is surrounded by the cladding. Now the most important is, if the light travels like this, right, and then it falls all the way like this, correct? And after that, this is considered as, this line is considered as core and cladding interface. Clear? Core and cladding interface. So without any second thought, I can say that the core has refractive index more than cladding here. So that means the core refractive index, if I say N1 and this is going to be N2, so I can say that N1 is more than N2. So there might be a chance that the total internal reflection can take place here. So therefore, how does the light will flow here? But whatever may be the situation, he is just asking what would be the critical angle at core and cladding interface. Now tell me, if I draw the normal like this, this is going to be considered as a normal to the interface, fine? Then this would be considered as an incident angle usually, right? Right now it must be critical angle, clear? So that means this angle must be critical angle with the core and cladding interface. What do you mean by critical angle? Any answer, Pramit, from your side? Have you got the answer? So at the interface, exactly, if it is a critical angle, then the light ray should propagate at a 90 degrees refraction, correct? Refractive angle is going to be 90 degrees. That means I must say that all the way it has to go just like this, clear? So that means if I calculate this angle, that is theta r, it should come like 90 degrees here. Now if I apply Snell's law at boundary A, let me write down, at boundary A, right, at boundary A, so let me write down capital A here. So at boundary A, if I apply refractive index, you know, Snell's law, apply Snell's law, Snell's law. So if you apply Snell's law, what will going to happen here? Any answer from your side? So it is theta c, and of course the core refractive index is n1. So therefore I can say n1 into sine theta c, undoubtedly that must be equal to n2 into sine 90 degrees. No doubt about this one, correct? Sine 90 degrees. And if you are clever enough, we can easily say that theta c is equal to sine inverse of n2 divided by n1. Clear? N2 divided by n1. Do we have n2 value and n1? Yes, we do have the values of n2 and n1, because we have calculated that in the previous question itself, correct? In the previous question, the same status, in fact the same data is getting continued here. So therefore theta c is equal to sine inverse of n2 is how much? The refractive index of the cladding, that is equal to 1.59, no doubt about that, and divided by, what about the refractive index of the core? Refractive index of the core is simply equal to 1.60, correct? So therefore I can say theta c is equal to sine inverse of, this value is how much? Just take your calculator. Any answer from any one of you? Please let me know. Final answer here, 1.59 divided by 1.60. All the way you will be having some value 0.99375. 0.99375. 0.99375. इसको sin inverse निकालना पड़ेगा, right? So anyway, finally I am writing the final value, because I feel that you people are capable to do this small calculation here. And what is the final answer we are going to expect here? So the final answer is going to be theta c, which is equal to 83.59. So let me write down simply like 83.6 degrees here. Clear? So the final answer for this question is option B, that is nothing but 83.6 degree. Many of you may be thinking that these questions are slightly easy, isn't it? But as the things are progressing, slowly you will get very, very good questions also. So wait for that time. Now moving ahead to the next one, that is, this is slightly better than previous two questions, but not so great question. But let me explain this. The velocity of the light in the core of a step index optical fiber is 2.01 into 8 meter per second. Right? Meter second inverse means meter per second. The velocity of the light in the core. So this is given. So let me break up to there and try to understand what is this. So we can all say that the velocity or the refractive index of the core is equal to n1, which can be written as the speed of the light in space or in free space, divided by the speed of the light, especially in that medium. So the speed of the light or velocity of the light in that medium, let me write down that as v1. So c is being the speed of the light in free space. Clear? And v1 is considered as the velocity of the light in the particular medium where we are using our core. Clear? So v1 is nothing but velocity of the light in the core. That's why you must understand, if the refractive index is more, the velocity of the light in that particular medium will be less, or the speed of the light in that particular medium is less. If the refractive index is actually low, then it means that the speed of the light in the medium will be high. Clear? So therefore, keeping that in the account, it is very easy to calculate n1. What is n1 here? C is, nothing is given, so let me take 3 into 10 power 8, which is considered as, speed of the light in free space. So divided by 2.01 into 10 to the power of 8. So therefore it gets cancelled here. So what will be the n1 value? N1 value, Pramit, any value, you got it? So you have to be fast enough, right? Yes. So it is going to be 3 divided by 2.01. So all the way you are getting like 1.49, right? So let me write down 1.492. That is the refractive index of the core. But you require to have the refractive index of the cladding to get the numerical aperture. Correct? How do we get that one? It is also simple, because in the previous step itself, in the previous case, when you remember this one, we have written exactly at boundary A, when we apply the Snell's law, we are going to have n1 sin theta c is equal to n2 sin 90. Same logic can be applied even in the middle of the second question also. Look at that. He himself told that the critical angle at the core and cladding interface is 80 degrees. What does it mean? It can be written now as theta c, which is nothing but the critical angle of the numerical aperture is 0.29. Very good, Pramit. So theta c, it could be written as sin inverse of, what should I write here? So n2 divided by n1. Correct? So now it is given like sin 80 degrees. So it is 80 degrees here. 80 degrees equal to sin inverse of n2 is how much? We don't know. So let me write down n2 here. And this must be 1.492. Right? So sin 90. So n2 is equal to 1.492 into sine of 80 degrees here. So therefore, I can say final value here is 1.492 into sine 80. Pramit, have you seen the previous lecture? Pramit, please respond me and tell me whether have you gone through the previous lecture, that is light sources and detectors. Please let me know in the comment section. 1.492 into sine, sine 80 degrees here. So what would be the final value here? Yes, 1.4693 something is there. So let me take 1.47 here. Yes sir, very good Pramit. So probably many students are not there in the live, but I am very happy that you people are utilizing the YouTube services properly. N2 is equal to 1.47. Therefore, what is the numerical aperture now? Now the numerical aperture is very simple. That is under root of n1 square minus n2 square. That's why I told you that numerical aperture depends only on the refractive index of the core and cladding, refractive index of the cladding. Therefore, if you go ahead and rewrite this one, how much you will be getting? Refractive index of the core 1.49. So 1.492 whole square minus 1.47 whole square. If you want, you can even find out clearly that the numerical aperture final value is equal to how much. So let me take calculator and do for every one of you. So it is under root of, yes, so 1.492 square minus 1.47 square here. So it will come something around 0.25. I am getting 0.25 numerical aperture. Please look at that and let me know, Pramit. I am getting 0.26 approximately. So please look at the calculator. Maybe some things we have a zoom. So maybe that's the reason it is coming like that. So if it is 0.26, what would be the acceptance angle? Because the acceptance angle is very important for us. Here 0.26 is the answer, and the acceptance angle when the surrounded medium is air can be written as equal to, so obviously it can be written as a numerical aperture is equal to sine inverse of, if the surrounding medium is air, we can write down 1 into, this value must be 1 into sine of theta A, simple. So let me write down clearly, yes, it is going to be 1 into, that means the refractive index of the air, into sine of theta A, that is the acceptance angle, correct? So therefore theta A could be written simply as a sine inverse of numerical aperture. So what is the value? Numerical aperture is known to you, 0.26, correct? So therefore sine inverse of 0.26, what would be the final value? So it is coming around 15.07. Even I have taken some kind of approximation here. So because it is not exactly 0.26, it is 0.255, something like that. If that is the case, maybe this answer may match with the option A. So therefore option A is the correct answer with our approximations. Okay. So hope these questions everybody of you can solve this. Why I have taken these questions, even though I know that my students can be able to solve very easily, because every time I am seeing, even though the entire paper is so complicated, you will be getting at least one question more or less from this topic. Clear? That's why it is better and wise to know in and all around the easy topic. Okay? Because if it is easy topic, we should not neglect that. Rather, we should clear that and fix that in our memory. Clear? So let's move on to the next question here. So the next question, now I am expecting the answer from you. Okay, Pramit. So look at that, if the above fiber is illuminated with the IR light, so that means it is a continuation of the previous question. This question, I am still continuing this one here, has a vacuum wavelength of 0.25. So let us not go with this one. So let us, if the fiber, so let us not use this one. Okay, let us take, because the numerical aperture separately I have taken, diameter also I have used. So let's try to do this question separately. Okay, fiber is illuminated with IR light that has a vacuum wavelength of very good 2.50 micrometer. Determine the numerical aperture and the diameter of the core is given like 125 micron. 125 micron, inherently it means that 125 micrometer. Clear? Now the first question is, what is the V number? V number basically it indicates, it is used to know how many rays we can transfer through a particular fiber. So how many rays that can be transferred through a particular fiber? Quite logically, it depends upon the numerical aperture, correct? So let me write down the V number which is used to understand how many rays that can be propagated through the fiber. Okay, so that should be written usually as the perimeter of the fiber. So that means if you have fiber like this, so it will be obviously a circular cross sectional area. So it is a perimeter is 2 pi r divided by the lambda which is going to enter, that means the photon wavelength which is entering into the fiber. Of course the V number will be directly proportional to numerical aperture. Why I am taking directly proportional? See, it is saying that numerical aperture. What does it mean? The more the aperture is, the more light can flow through that, more number of light rays can flow through the fiber. It's very simple logic. Therefore the V number should be directly proportional to the numerical aperture. So the V number, logically it indicates that how many light rays that can be forwarded or that can be launched through the fiber or can be propagated through the fiber. If more number of light rays can be propagated through the fiber, we say that the value of V number is high. Clear? Simple. So therefore I have written that V number is directly proportional to numerical aperture. However, it also depends upon the perimeter of that. So 2 pi r. If more the perimeter, so obviously more the perimeter means it looks like this. Correct? So that's the reason why it is directly proportional to 2 pi r and even numerical aperture also. So therefore this can be considered as a formula. Of course, if anybody want to know what is the proof for this, you can refer my lectures which are available on BYJU'S Exam Prep app. Just download this app, BYJU'S Exam Prep. There, yes, V number is nearly equal to good. So download this app. There you can find the instrumentation lectures. Go to optical instrumentation lectures. In that, go to the topic called light propagation through the optical fiber. There I have explained about this V number concept and all. Clear? So therefore, if you go ahead, what is V number here? So 2 pi r, it can be written as, instead of writing like this, even we can directly use the diameter also, pi into diameter divided by lambda. Numerical aperture can be given as, of course, numerical aperture is directly given. I am extremely sorry, right? The numerical aperture, you can take the previous value itself, that is 0.2588. Good. All the values are there. So what should I say here? Pi is 3.14 approximately into 125 micron. 125 into 10 to the power of minus 6 here. Wavelength is how much? Wavelength lambda, where is that? Yes, 2.50 micrometers. So that is 2.50 into 10 power minus 6 into 0.2588 here. Correct? So this will get cancelled. So therefore V number, finally it will be equal to how much? Number of modes 825. We'll see whether you are right or wrong. 3.14 into 125, right? So 125 all the way you will be having some value into 0.2588 divided by 2.50 here. So therefore it is very simple to say that 40.63 you are having. Clear? So this is V number. But how do we find the number of modes that can flow through the or propagate through the fiber? See, we won't propagate all the light rays which are capable of the optical fiber. We will limit ourselves. It is simple to understand. Suppose assume that my capacity is to eat 10 laddus. 10 laddus I can eat, right? That is my capacity. But it is not advisable to eat all 10 laddus and sit, for some times or sleep for some time. What I do? I will always try to prefer less than 10 laddus so that I will be active enough. Correct? So similarly here, though we know that we can transfer or we can propagate many modes through the optical fiber, we will limit the number of modes always as equal to, so please see here, which is equal to the V number square divided by 2. Clear? Half of V square. That is a general, thumb rule what we will be using here. So what will be the value here? So it will be 40.63 whole square divided by 2. I think Pramit is correct. So he is very fast also. Good. So 40.63 into 40.63. So there will be some value divided by 2. Simple logic. 825 I am getting approximately. Yes, 825.4. This is the value I am getting roughly. So this many number of modes that can be propagated to the fiber. So these two questions seems to be very important because most of the students, they can't remember the formula for the V number. I have given the logic. V number will indicate easily that the number of modes that can be propagated through the fiber. So naturally the number of modes which are propagated through the fiber, it must depend upon the circumference of the circular circumference of the fiber. That's why it is multiplied with the 2 pi r, or it is directly proportional to the 2 pi r. Along with that, the numerical aperture. Now I have a question, Pramit, to you. Tell me, if the diameter of the core is less, if DC, diameter of the core, let me write down diameter of the core is low. If the diameter of the core is low, whether we can transmit the more number of modes into the fiber or less number of modes into the fiber. What is your question? Can we transfer more number of modes or less number of modes? Suppose if at all, it's logical, right? It's very much logical. If diameter of the core is less, naturally this value, the numerator value will be low, correct? So this value will be low. If this value is low, obviously V number will be low. If V number is low, then the number of modes that we can transfer or propagate through the fiber will be low. Clear? That's why people do say that if at all the diameter of the core is so less, it is considered as a single mode optical fiber. Clear? If the diameter of the core is so less, in the order of micrometer, then we call that as a single mode optical fiber, because we can transfer only one mode as the diameter is very, very less. So if you want, for special applications, usually we prefer single mode, but in general, in practical applications, we can only go for the multi modes. Clear? So moving ahead to the next one. This is, I feel that this is one of the good question. So let me see how fast you can answer this. As shown in the below figure, the attenuation of an optical fiber line with the length of 12 km is 2.5 dB per kilometer. Good. Attenuation is given like 2.5 dB per kilometer. Good. The radius of the fiber core is 5 micrometer. Good. If the optical power at the input of the fiber is 300 micrometer, what is the output intensity at the output of the fiber is dash. So now, sir, for single mode fiber, the V must be 2.40. Not exactly. So it is almost. Clear? It is almost, right? So what is the output intensity? I understand from here you have done that, right? You made it as 1 here and V square something you have done and got it, right? But generally we will be nearby, operating near to that value, 2.4. Okay. So here what we should do here, first of all, you must understand that the length of the optical fiber, all the way it is given like L is equal to how much? 12 kilometers. So write down that one, 12 kilometer. What is the attenuation coefficient or attenuation here? Attenuation, how much is the attenuation coefficient value? Attenuation is given as, so just look at that, it's given as a 2.5 dB per kilometer. Wonderful, 2.5 dB per kilometer. So the total length is 12 kilometer. 12 kilometer lengthy optical fiber we are having, huge amount of length, correct? 12 kilometer is very large, right? So 2.5 dB you are going to lose for every 1 kilometer. This is the meaning of that. So usually the attenuation coefficient must be in, negative, right? But we will take another formula. I'll show it to you. 2.5 dB. So can you tell me what is the total attenuation now? Now the total attenuation could be written as how much here? So 2.5 dB by kilometer. Of course, it must be multiplied by 12 kilometers here, right? So without any second thought, I can say 12 into 2.5. How much this value will be? So 12 into 2.5. So 2.5 into 12. I would say this is equal to 30 dB. Clear? 30 dB is a attenuation here. 30 dB is a attenuation. But how do we write the relation between the output power and input power? So usually if I say this is the input power here, P in, and let me say this is the output power, P out. Clear? Input power and output power. What is the attenuation formula? Attenuation in dB can be written as, attenuation in dB could be written as 10 log the input power divided by the output power. Clear? Input power divided by output power. Look at that. In every sense, we usually do like output power by input power. But in optical fiber, we must write input power by output power because the attenuation is taken as a positive number here, 30 dB. Usually it is quite obviously the output power will be less than input power. You don't require the rocket science to understand this, because whatever the power you have emitted here, some of the photons will be losted or some of the photons will be transmitted or scattered inside the optical fiber. Naturally the output power will be low compared to the input power. So that is very clear. So if the output power is low compared to the input power, if you take 10 log, okay, output power divided by input power, then the attenuation will going to come as a negative value, correct? So it comes like a negative value, right? But it's given like attenuation all the way we got positive number here. Therefore, this is not the formula what we should use. This is the formula what we must use. Clear? This is the way how you should think, right? Now attenuation is 30 dB, all the way it's given like 30 here and 10 log. So here the input power divided by output power here. So what should I say here? So it is going to be 3 and 10 power 3. So therefore I should say, what is the value here? So it is going to be 3 times it gets cancelled here. So undoubtedly, correct or not? So 30 dB I have made it. So 30 is equal to 10. So it will be 3 dB and 10 cube. So 1000. Okay. So if you apply 10 cube is equal to, one second, right side you will be having 10 cube is equal to Pi, the input power divided by the output power here. So but look at logically, what was the input power? The input power is given to you. Yes, the input power is 300 micrometer. It's given. If the input power is 300 meter, yes, correct. Output power is 0.3 microwatt. Good. So the output power could be written as input power here divided by 1000 here. Correct. So it is already mentioned that 300 microwatt. So if you use 300 microwatt divided by 10 power 3, it could be easily said as a 0.3 microwatt. That is 10 power minus 6 watt. Clear? So 0.3 into 10 to the power of minus 6 watt. So after this much of hard work, we just got the output power. But how do we calculate the intensity? Intensity, how do we calculate? Suppose if you take all the way, this is the output, right? Let's assume that we are all the way getting the light like this. Of course, it's not possible to get the light here. Suppose in case if I keep something here, what would be the intensity? That can be maximum falling on this one. The intensity of the light which is falling here could be written as the intensity. Any one of you, what is the value of intensity? So now I have given all the way up to 99% of this question I have solved it, right? So you know what is the output power. You are required to calculate the intensity and select the correct option. Any one of you, Pramit, what is the answer? Any answer from your side? How do we calculate the intensity? So this 1% I am leaving as a homework to you, okay, because 99% I have solved. So the intensity always can be given as how much amount of the power that is falling on a particular area. Clear? So if you take some kind of surface here, right? So let us assume that all the way, so it is falling on this particular surface, right? So it will naturally form the circular cross-sectional area here, right? Power for area of cross-section. Good. That is considered as the intensity. So the power for the area of cross-section, right? So it have to be assumed that the full area, circular area is covered here, right? So therefore, I should say that the overall power here is 0.3. So let me write down fadafat here. So 0.3 microwatt here. One second. So the intensity is 0.3 microwatt, 0.3 into 10 to the power of minus 6 divided by a circular area of cross section. How can I write? So this would be like a pi into d here, right? So where d is the diameter here, that is 5 micrometer here. So use the diameter here as a 5 micrometer and solve this algebra. You will be getting the option, that is option B is the correct answer, that is 0.38 watt per centimeter square. Simple question, correct? But you must not use the formula like this. Rather, you should use this formula. Many students, they get trapped by using this formula and finally do the mistake, and instead of getting into IIT, they will come to NITs, or else instead they will waste for the next 1 year, or they will come to the coaching once again. Clear? So Jayanta Pahari, option B, very good, excellent, right? So now Jayanta Pahari, good. Option B is the correct answer. Now let me give another question to you. I want to give this question as a homework, but as I have the time, so let me explain briefly about this question, because this is a good question where you can see the light is propagating all the way through the medium and finally landing on the detector. So therefore, we should know how the light is propagating into the fiber, from where the light is coming, how the photons are entering into the into the fiber, and what is the bandwidth of the detector, what do you mean by the bandwidth of the source. All these concepts are very, very, very important. Whatever the questions we have solved now, more or less all the questions are directly on the formulas. But there is a lot of physics that is involved behind that formula, and being an engineer, it is your responsibility to go through all the concepts which are behind that formula. Then only you will enjoy the optical instrumentation concepts. And if anybody is seriously interested, you can refer my class lectures in BEP app. That will really help you. Anyway, let me do this question. One end of the step in is multimode. Look at that, multimode. Whenever I use the multimode, the light will come like a beam. Okay, the light, output light will be like a beam. It's not like a ray. You will not get a single ray at the output side. You will get a beam of light. Beam means it will include a lot of rays. Clear? Lot of rays. Optical fiber is connected to a pin photodiode. Good, very good. The area of the photodiode is large enough to capture all the light emitted out of the fiber. Excellent, very good, right? So the data for the fiber and the photodiode is as followed. The core refractive index is given, cladding refractive index is given, and the wavelength is also mentioned. Good. So attenuation is 800 nanometer. So attenuation at 800 nanometer, that means at this wavelength it is equal to 10 dB per kilometer. But however, the length of the fiber is very low, that is just only 10 meters, right? So pin photodiode has, at the same wavelength 800 nanometer, the responsivity is 0.55 ampere per watt. Have you seen here? Whatever the wavelength of the ray, light ray, that is propagating to the optical fiber, we are selecting the photodiode which has a central wavelength of the same wavelength, correct? So why do we select like this? Any one of you, Pramit and Gajendra. So there are so many students are there, Gajendra, Pramit and Jayanta. You please let me know, why do we select the wavelength of the pin photodiode and the light ray which is traveling with the same wavelength? Any one of you? Because look at that, usually we will have the fiber like this, correct? Fiber like this. So we all know that the output light ray, so if I say this is the axis, the light ray can come like all the way like this, right? So if it is the optical fiber is multi-mode, then quite logically the fiber will be coming all the way from the edges also like this, clear? So much amount of the light will be coming here, right? So now the crazy part is, when the light is coming out of this, it will definitely fall on the detector. So as he is saying that the detector is large enough to capture all the light, it was mentioned clearly. So we don't require the lens also. We don't require any lens here, because the detector itself, it is highly capable to capture all the light. So let us say we are having the detector here for time being. Okay? So the detector also present here, right? As the detector area, surface area is very high, even though the light is coming all the way out of the fiber, it can capture the whole light. But you must understand, the detector sensitivity is high only if the wavelength of the light is 800 nanometer. Clear? So that means this detector can provide responsivity of 0.55 ampere per watt only when it is reaching, or when the light or when the photon is having 800 nanometer. So the first important and foremost important point is, responsivity is the function of the wavelength. Clear? The responsivity is the function of wavelength. That means if you use the same detector here, but if you change the wavelength here, so assume that you might be changing the wavelength here, so the wavelength of the light which is coming out. So if I say the lambda is equal to 600 nanometer, what will going to happen? Unfortunately, if the wavelength which is propagated through the fiber is having 600 nanometer, but the detector has a capacity to give the maximum sensitivity at 800 nanometer, what will going to happen? Detector will say to the fiber that, please give me the light ray which has a 800 nanometer. At that time, I can provide the maximum sensitivity. Correct? But an optical fiber will say that, no, I don't have that kind of wavelengths. I have the wavelength of the light ray which is of only 600 nanometer. Then what will happen? Detector will not satisfy. Detector cannot provide the high responsivity. This is the reason why in optical instrumentation, the first device what we will buy is a light detector, and we will know what is the wavelength it can give maximum responsivity. So at this point it is 800 nanometer. That time you should go back to the LED here, that means light source here, right? Of course we will going to have lens and all these things here, light source, and the light source lambda should be how much? It is advisable even if the light source is also generating 800 nanometer single wavelength. That means let us collect or let us select, okay, let us select a light source which is of monochromatic, means it can generate only single wavelength, but that wavelength must be 800 nanometer. If it happens, then only the 800 nanometer will propagate through the fiber here and it will come out of the fiber, correct? And then that will be falling on the detector. So obviously the wavelength of the photon will remain same throughout the journey, but the number of photons may be changed. Clear? I repeat here, suppose if I say the wavelength of the light ray coming from the light source is 800 nanometer, assume that all the way it is propagated towards this one. Output side also it will going to be having the wavelength is 800 nanometer only. That means the wavelength will not change. I am absolutely confident that the wavelength will not change. But fortunately, right, wavelength will not change. Fortunately, the number of photons will change. When the number of photons will be changing, that means here if the number of photons are 100, for example, number of photons are 100, what will be the total energy at the emitting side? Total energy will be equal to n into hc by lambda, correct? So, but at the same time, if you see output side, maybe the number of photons here, so let us say the output side here, the number of photons, let me say small n, which is equal to 50. What does it mean? The total energy at the output side, obviously it will be equal to simply like 50 into hc by lambda here, and here it is going to be 100, isn't it? So that means, what is the conclusion of the story here? Why I am explaining all these things here? Can you think and tell me? It means that energy is high at the entry side, but the energy is lost at the output side because some amount of photons may be absorbed by the core material, or sometimes it happens that through the cladding, the light rays or the photons get scattered, right? So that means some photons may try to go like this, okay, it is also possible. That's why we need to have proper insulation around the cladding material, such that the photons cannot escape from the medium. All the photons will be there, so that we will be having the less power loss or less attenuation. So the energy will be same at the input side and output side, but quite obviously it will not happen. It will not happen. It will be never happen, right? So that's why the input number of photons at the input side and the output side both will be different. So the energy at the input side and output will be different. So the power at the input side and output side will be different. Usually the power at the output side would be less than the power at the input side. Clear? Power at the input side. Hope you understood. Please let me know, all of you, Gajendra Singh, Pramit, Jayanta and Isha Agarwal, please let me know, is it clear to all of you? I think I have discussed one step beyond the requirement. Hope you really enjoyed with that, right? So now you must understood clearly that whenever your detector has the maximum responsivity at, yes, understood, right? So when the detector has a maximum responsivity at 800 nanometer, it is your responsibility to select a optical fiber which has a less attenuation at 800 nanometer. That is the first thing. And a source which is monochromatic at 800 nanometer. These are the two prime conditions you should make, and the choice of the optical fiber and the source will be decided based on the kind of detector you are having in your lab. Clear? You are having in your lab. So that is the basic point. I hope I made it everything clear. Now you must understand the detector, that is pin photodiode, has a responsivity of how much? 0.55 ampere per watt. What does it mean? If 1 watt of power is incident on the photodiode, it is capable to generate 0.55 ampere. That means now we must know how much amount of the power of the light that is going to incident here, power will be coming onto the detector here. What is the power of the light? So that is P out, let me say. So therefore I should say, casually it is very simple to understand. So the P out should be calculated. P out of, optical fiber, it is actually equal to what? It is equal to PID, that means input power to the detector of detector. Input power of the detector. So that means our goal is shifted. First you need to calculate P out. How do we calculate that one? We all know that the attenuation could be written as attenuation all the way. That would be equal to 10 divided by, in fact I should say the total attenuation in dB, right? So what is the value of the total attenuation in dB here? So the total attenuation in dB would be equal to 10 into logarithmic of the input power divided by the output power. So input power divided by the output power, right? So input power divided by output power. So how much it will become now? 10 logarithmic of input power is given. So 2 milliwatt is launched, means it is going to be 2 into 10 to the power of minus 3 divided by the output power here. Good. That is also clear. Correct. Now what is there in the left hand side? Have you seen? It is attenuation coefficient is how much? They mention like 10 dB per kilometer. 10 dB per kilometer. But right now the length is only 10 meters. Correct. So therefore I can say attenuation coefficient is attenuation coefficient, let me write down, it is 10 dB per kilometer. That means 10 dB for 1000 meters. That is the meaning of that. Correct? 10 dB per 1000 meters, right? 10 dB per 1000 meters. But for 10 meters, how much it will be? So I think it will be for 10 meters. So let me write down for 1000 meters. So it's very easy from the given logic here. So we can say very confidently, just give me 1 minute time here. So here, if you have 1000 meter length, the attenuation would be 10 dB. Correct? This slope is constant. However, if you have only 10 meter, what would be this one here? So 10 into 10, that is 100 dB by 1000. So this will be 0.1 dB here. Clear? So this is also easy, 0.1 dB. Sir, please take a separate session on Venturi meter and YouTube manometer concepts. Some concept questions, sir, please. Okay, Premise, sir, responsivity and sensitivity is same or different? Jayanta, yes, responsivity and sensitivity for pin photodiode is same. And if you want to know, you can refer the previous lecture that was taken yesterday only. There I have explained clearly what is called responsivity, how it depends on the wavelength, and why we call responsivity and sensitivity both are same. In case of pin photodiode, both are same. Sometimes we call sensitivity, sometimes we call that as a responsivity. Clear? Please take a separate session on questions mixed with Venturi and YouTube manometer. Okay, Pramit. So that's why I'm saying that your requirements you can please post in the comment section after the session is completed. Then we will collect all the responses from the students, and based on the demand we will go with that sessions. Correct? So now, we understood that 0.1 dB is the total attenuation here. So let me write down 0.1 is the dB. Therefore, if you go ahead again, 10 will come here. So the 10 will come here, 0.1 by 10. So it is very, very less value. I am extremely difficult to see what will going to happen here. But anyway, this value is 0.01. Correct? So finally, 2 into 10 to the power of minus 3 divided by the output power, that would be equal to what? 10 to the power of 0.01. Correct? So 10 to the power of 0.01. What is the value here? So 10 to the power of, so once again, 10 to the power of 0.01. So its value will come down to be 1.02. So the P out, the output power now could be written as 2 into 10 to the power of minus 3 divided by, this value is going to be 1.023. Clear? So what's the value here? So it is divided by 2, I can take and then reverse it. So 1.95 approximately I am having 1.95 into 10 to the power of minus 3 watts. Clear? This is the output power. Yes, correct. Very good. So this is the output power what we are receiving specially from the fiber. And this output fiber, that output power straight away given as the input power to the detector, because it was mentioned that all the light that is coming out of the fiber is collected by the detector. So there is no power loss here from the end of the optical fiber to the detector. So that means whatever the power of the light, power that is coming out of the fiber, fully the detector is able to capture. But what is the responsivity of the detector? 1 watt can generate 0.55 ampere. This is the catch here. Correct? Therefore, I can say clearly that if at all the power is 1 watt, it is capable to generate 0.55 ampere current. Very good. But what is the power now? 1.95 milliwatt. 1.95 into 10 to the power of minus 3 watt, it can generate how much amount of the current. So the output current or the photo current, whatever we are going to get, that could be written now as simply equal to 0.55 into 1.95 into 10 to the power of minus 3 ampere here. So what is the final value here? So the IP value could be written as, any one of you got the answer? I will be very happy if you give the answer. Anyway, I thought of giving this to homework, but I made myself. So it's coming around 1.07. 1.07. Just check the calculation and please let me know everything is correct or not here. So IP is equal to 1.072 milliampere. That is the answer for this question. The last question what we have solved here is comparatively better question that I feel it's a gate level question. In fact, majority times the questions, especially in the optical fiber, they are very simple. Okay, they seems to be very simple, but very rarely you will be asked a good question. So if you want to refer the good questions and challenging questions on optical fiber, you please refer my classes on the optical fibers. At the same time, try to attend all the practice sessions which I am going to take in rank up course. Okay, so to understand the details of the rank up course and all these things, you can actually connect to me through the Telegram channel. So I will try to explain, or else you can directly message me, so that I can tell you what is the meaning of rank up course, how many practice questions we are going to solve. Definitely I can assure you that you will see a different level of instrumentation if you are attending the practice sessions taken by me in BYJU'S Exam Prep app. Hope you really enjoyed all the sessions related to the champion series. Once again, I am saying this, Jayanta is asking some questions, sir, please take a lecture on YouTube manometer and venturimeter. Good. So I think many people are, I have never understand the source fiber detector in depth. Everything is cleared. Thank you very much, Gajendra. Nice comment. I really enjoyed your comment. So that's why I'm saying that you will definitely see a different level of instrumentation completely if you are attending the practice sessions. And I will be taking the practice sessions on industrial instrumentation, process control instrumentation, optical instrumentation, all these three in the next 50 to 60 days, every day for 2 hours approximately in BYJU'S Exam Prep app. If you want to know clearly the details like when the timings will be, what is the starting time, what is the ending time, how many students are coming and all these things, you can directly message me by using these Telegram credentials, so that I am ready to help you at any particular time. So I am taking your points, and I noted that you are requesting me to take the lecture, separate lecture on YouTube manometer and venturimeter. I will definitely take those 2 lectures, but you follow me so that you will be able to understand when I am going to take that lectures on the YouTube. Clear? So hope you really enjoyed with this lecture. And once again, I am saying that I have provided the credentials of the Telegram link, and it is your responsibility. If you are so sincere for the GATE examination, if you are so dedicated, if you are so much serious student, obviously you will be having better destination only me. Clear? So fine, we will be meeting once again in the YouTube based on your demand. Till then, bye bye, take care.